What's up, everybody? My name is Shreyas, and today we're going to discuss the problem the delicious cake, which is asked in June Long Challenge 2020. The prerequisites for this problem is the knowledge of cross products and literally nothing else, only that much. So you guys may be thinking this will be a very simple question, but if you look at some stats over here, only at the end of the contest it was only some 250 people who had got 100 points. So this is a very interesting problem. Let's have a look at it. Okay, so we're in the problem statement. I have simplified the problem and condensed it in this document. So what we are given is we are given n points in a 2D plane, and a layer is a simple polygon which is formed by connecting some or all of the n points, and we are given a separate point which is called as the candle point. Okay, this is given later in the query part, and we need to construct the layers in such a manner that the number of layers which completely enclose this candle point is as large as possible, right? So I hope the question is clear to you. Yeah, and there are some certain set of rules to be followed. Each point can be a part of only a single layer, and no two layers can touch or intersect each other, and all the point that lies within some given layer must be a part of some other layer, or they must be the candle point itself. So they must be in participation, they can't sit idle there. Okay, so this is the rules, and obviously the goal is to maximize the number of layers. Okay, cool. So let's look at some examples before starting. So in this 2D plane we are given some set of points, and this configuration of polygons is initially done by me, so this is just random configuration just for the sake of explanation. So I have drawn these 6 polygons, and they satisfy all the rules because they don't touch or intersect, and all the rules are satisfied. And suppose in the query, if they're given the candle point to this point, okay, so as we can see, no layer actually encloses this candle point, right? So the answer is 0 actually. So can we trace the reason why the answer is 0? Like it has to lie within the fashion like how we construct the layers, right? So all the layers here have very small areas. So what does that imply? So small area implies smaller probability of the candle to lie within that area. Okay, so how can we do better, right? So obviously the way to do better is to draw larger areas. So suppose if we increase the area of this layer and connect these 4 points, this layer encloses this candle point, right? And similarly, if we connect these points and form another layer, so 2 layers now are enclosing the same candle point. And finally, if we also include this layer, 3 layers are including this candle point. So the answer now becomes 3. So what have we done? So we are just trying to increase the layer area of the layers. So larger the area, larger the probability that the candle point will lie. Okay, so that's not the sole criteria, but it's one of the important reasons. So next is, how can we increase the area? So obviously by connecting farther points we can get a larger area. So in this case, for example, see the outer layer, we connected all the farthest points and we have got the maximum area possible, right? So by the optimal layer will have the farthest points connected among all the remaining points, right? So what does it imply? So it also implies that for a given layer all the remaining points will lie, for a given layer, if it's an optimal layer, all the remaining points will lie inside of that layer. Okay, so for example, in this example, the remaining points lie within the outer layers, and that is valid for each layer over here. So that is observation number 1. We need to maximize the area. So observation number 2. Suppose in this case we have drawn 3 layers. Layer 1 is the outer wrapping layer, layer 2 and 3 are adjacent layers. Okay, so now suppose if there are three candles, so the answer for candle 1 is 2 because layer 1 and 2 enclose it. Answer for candle 2 is 1 and 3 is 2. Okay, So we'll try to optimize it. So suppose if we suppose if we draw a larger rectangle and over here as well we connect the smaller dots. Now these areas are not there, these lines are not there. So now the answer for 1 remains 2, but the answer for 2 actually increases to 3. Initially it was only 1, now it becomes 3, and then for 3 it remains 2. Okay, so what is the lesson we can get from this? So by drawing concentric layers one inside other, we are not doing any worse than drawing adjacent layers, but in some cases we are actually doing better than drawing adjacent layers. So that's the lesson number 2. So keeping these two things in mind, now next we'll try to draw the layers, right? So yeah, so suppose in the input they have given all these input points to us. Now how do we construct the optimal layer that we had discussed previously? So remember, the optimal layer is the layer which all the remaining points should lie within the layer. So that's the main foundation of this thing. Okay, so now, like, it's not hard to say that the point with the least x coordinate should always be the part of the layer, right? So in this case, this point, right, the point with the least x coordinate. Okay, why is that so? So like, if we try to prove by contradiction, suppose if we ignore that point and just form the layer without it, so this is the layer, right, without it. So what is happening, this layer is not an optimal one because there's one point out of this layer, right? So that shows that the point with the least x coordinate should always be included. So we have got our first point. Now from the first point, how do we obtain the next best point? Okay, so let's call this point A. And how do we obtain the next optimal point? We can either go in the clockwise direction or we can go in the anti-clockwise direction. So for the sake of this problem, we'll stick to clockwise direction. So let's draw a demarcation over here, and let's focus only on the upper quadrant, right? Cool. Okay, so suppose there's a torch of light over here, and then suppose I send rays of light to the upper quadrant, and suppose I send rays of light till over here. So what it means is I can see all the points which are lying in this region, and all the points lying in this region are not visible to me, right? So if I proceed to form the layer by only taking these points, then that won't be the optimal layer because these points are not included, right? So we need to send the rays of light to the leftmost point. So this is the leftmost point, and this will be the most optimal point. So once we do that, we can confirm that this is the most optimal point because there is no point to the left of it. So in other words, in a simple manner, the point which makes the maximum angle in anti-clockwise direction with respect to the initial point, that is the next optimal point. Okay, so so since we found out the next optimal point with keeping this as the current point, we need to repeat the same process. So it's not hard to see that this point will make the largest angle with respect to this A right over here. Okay, so and repeat the process. So yeah, at all points this is valid. This is the only sole criteria for the selection of the next point is the angle. Like for example over here as well, this one is the max angle, right, in anti-clockwise direction. So we select this vertex. Okay, now that we have completed forming a so when we reach the starting vertex, that is the time we need to stop proceeding further. So that is the time one layer is formed. So we need to store this layer in some data structures like a vector or an array, and then we need to come back and form layers with the remaining point. So from the remaining point, again pick the point with the lowest x coordinate, in this case this one, and just repeat the same process. So we'll get this as the second layer. Okay, so this is how we do it. Okay, so how do we actually find, given the least point with the least x coordinate, how do we actually find the next optimal one while coding? So one way is to use trigonometry and find the angles, but there are precision issues in using trigonometric functions. So we'll use a more elegant way, and the way is that of cross products. So all of us have studied cross product in the high school, and so if there are two line segments AB and AC, so cross product is greater than 0 if it's clockwise, and less than 0 if it's greater than 0 if it's anti-clockwise, less than 0 if it's clockwise, and 0 if it's collinear. Okay. So how do we use it over here? So say we take a random point R. So this is some random point R we take, and then we draw a line segment from A to R. Okay, so now we know. So let us name this as point O. So now we know O is the with respect to A, O is the most optimal point, right? So how do we go from point R to point O? So that's the question. So what we do is we just iterate through all the remaining points, and then so suppose while iterating we find this point. For example, we find this point B. We just draw a line segment from A to B. Okay, so now the cross product of AR and AB will be greater than 0 because it's anti-clockwise, right? So we are going from like this, right? It's anti-clockwise direction, so the cross product will be greater than 0. So what does it indicate? So if the cross product is greater than 0, that means the current vertex B is always a better choice than the previous vertex R we had, right? Because it makes a greater angle with respect to A. Okay, so now with B as a random vertex, we just iterate through all the remaining points and just try to optimize the solution. So that will continue until we find this point. So this is the most optimal point, right? Okay, so now keeping this optimal point as the random point, we cannot find another point which has a cross product greater than 0. Okay, so hence we decide this is the most optimal point. Okay, so we repeat the same process for all the. So we got the line segment AO now. Now we keep our focus on this point O, and with respect to point O, again we repeat the same process as we did with point A, and then we find out the next vertex, and similarly and so on. And we can easily construct this convexel. In other words, layers. Yeah. Okay, so let's discuss the time complexity of constructing these layers. So for each point, in the worst case, all the points might lie on the boundary only. Okay, so for each point we are iterating through all the other points, and then we are finding the most optimal point, and there are n such points. So for each point is O of n. For n, so there are n such points, it will be O of n square. So the construction actually will take O of n square time. Okay, so we are done with this. Now there's a special edge case that we need to take care of. Suppose a line in the layer has like 3 or more collinear points with it. So what happens if we don't discard some of the points? What will happen is those points, if not discarded, they might participate in the layer formation of the next inner layer, and hence it will violate one of the rules because those two layers might touch each other. So what we do is we only try to keep the end points, and then we discard all the inner points. So in this case, if AC is less than AB, we just discard this point C. Okay, so and if AC is greater than AB, we just discard this point B and then assign random to this point C. So this is done basically to avoid multiple layers to touch each other. Okay, so this is one edge case. So now we have learned how to construct the layers, and then we have taken care of the edge case as well. Now we can go for the query part. Okay, suppose there are 3 layers over here, 1, 2 and 3, and then there are candles at position P, Q and R. That is the query. So consecutively we are given query points. So first P, then Q, then R. We need to find out how many layers completely enclose this point. So how do we do that? Again we use the property of cross products over here. So consider a line segment AB. Consider line segment AB and then line segment AP. So if we take cross product of this AB cross AP, and if we get a negative cross product, that means the point P is lying within the point P is lying within the line segment AB, because if it's clockwise it's negative, right? So we have already seen over here. So if it's clockwise direction it's negative. So this property must be satisfied by all the line segments of the layer. So for example, if we take this line segment, if we construct AB and AP, even for this, the cross product of AB cross AP is negative. It's in the clockwise direction. Okay, so if all the line segments of the layer satisfy this condition of cross product being negative, only then we can say that the point is actually within the layer. Even if a single line segment does not satisfy this condition, then even then the layer does not contain this point. It's really important for all the line segments to satisfy this condition. Okay, as another example, we'll see a counter case where this is not satisfied. Suppose in the layer number 2, as we can see, the candle point P is out of the layer number 2. So how do we determine that? So we draw this line segment AB over here as usual, and then we draw AP over here. So AB cross AB cross AP is actually it returns a positive value to us because it's in the counterclockwise direction. So when it returns a positive value to us, we can be sure that the point P is out of the point A, outside the point outside the line segment AB. So now is there a necessity to confirm this for all the remaining line segments of layer 2? And the answer is no, because even if for one line segment if it doesn't satisfy, then the answer is no. Okay, so we just go from the outer layer to the inner layer, and then there's a trick over here. So suppose for any outer layer, for any layer, if it doesn't satisfy, then we don't have any necessity to go to the further inner layers and check, because they will also not satisfy as they are already enclosed within the outer layer. So that is one optimization technique. Okay, so let's discuss the time complexity of this one. So there are a total of n points in all the, including all the layers, there are a total of n points, and then in the worst case we might have to check all the n points, right? N minus 1 line segments and n points. We might have to check all of them. So for each query it might take O of n, and there are q such queries. So in the worst case it may take O of q into n. So there is a way to optimize this to in logarithmic time complexity by using binary search, but for the given constraint this will hold good, and this is a very simple method, right? So the total time complexity will be O of q into n plus O of q into n for the query, and then O of n square for the construction. So it will be O of q into n plus n square. And next we'll look at the code. Okay, so here is the code. So first I'm like most of the other guys, I'm also using a short form for long int as LL, and we'll come to this function struct pair hash later. So first what are we doing is, this is a normal input what we are taking, and we are declaring a unordered set over here. So why are we using unordered set? So suppose I'm iterating through some points. I need to know whether that point has been already used by the outer layer or not. So for that I'm using the unordered set, and unordered set has a very good time complexity. Like in the average case, it has order like big O of 1 delete and big O of 1 search time complexity, so it scales very well. So for that case I'm using unordered set. And since unordered set does not support the data type of pairs, like we need to include another function called pair hash. So this is this function called pair hash. So the purpose of this function is to in order to put the pair in the set, we need to use this function. Otherwise, without this, it doesn't support. And this function is easily available on Google, so anyone can access it. And then we are just declaring the input array, and all layers will store all the. So suppose if there are 5 layers, it will store all the 5 layers in it. So it's a vector of vector because it stores individual vectors itself, right? So next we take the input, and then we insert them into the set. So our aim in this problem is to maximize the number of layers to be formed. So we'll completely exploit all the points, and so this condition is while the set is not empty, we'll just keep forming the layers as much as we can. So as we discussed in the video, we are finding the first leftmost point. Initially the leftmost point, we are initializing it to some really huge number, and then we are just iterating through all the other remaining points. And then so if the input point has a lesser x coordinate than the current leftmost point, then we just change the leftmost point to the input point. Otherwise, if it has a equal x coordinate, we just sort it by the lesser y coordinate. So this was explained in the video as well. And then I just assign the current variable to the leftmost. Here we take 2 more vectors. So one is collinear is for dumping the unused points in the same line, and then layer is for to include the points of the current layer. Okay, so anyhow we know the current point, that the leftmost point will always be a part of the layer. So here only we just push back into the layer. So this step is just pushing back the the point with the least x coordinate. Okay, so now as I said in the video, we need to just keep searching for the farthest points as much as we can until we reach the leftmost point once again. So actually the condition is over here. So if the current point reaches the leftmost point, that means we have come back again after the entire rotation. We have come back to the same point. So only at that time we need to stop forming the layer. Until then we must keep searching for the farthest points. So yeah, so the problem of giving the same condition over here is it will never start the loop. Okay, so I gave true over here, and then inside the loop I gave it. Okay, and then so next is to find the random vertex as we did in the video. So we just initialize it with -1, and then whichever vertex we get the first, and whichever vertex is not yet used in the some outer layer, we just assign it as random, and then we just need any vertex, so we just assign as random and then locate its position and then break from it. Okay, so now we have the current point, random point. Now we need to iterate through all the remaining points. So we just go from location +1 till n, and if that point has if that point is already the current point, means there are some chances, like if we might just iterate through the current point as well, so that's not a valid point. Or if it's already used in the outer layer, we just continue it. Otherwise we just take the cross product. So the function for cross product is really simple, what we have studied in the high school. So we just returns x1 y2 minus x2 y1. There's nothing much to explain in it. So if cross product is less than 0, then the random point is a better choice than the input point, right? Because it will make a larger angle than the input point. And if cross is equal to 0, I just called a function called distance, and it will return me true if the input point is nearer than the random point. So if it's nearer than the random point, then I just discard it. So to discard it, I'm pushing back in this collinear vector. And if it's farther than the random point, then I just push back the random point to be discarded, and then I set the new random point as the input point. Okay, so the distance function is also very simple. It's just calculate the distance and returns whichever is nearer. Okay, so after we are done with it, so as you can see, we are iterating through all the remaining points to find the most optimal point. So after, when we are out of the for loop, we are our random point so after we are out of the for loop, our random point is the most optimal now. Okay, so if there is any collinear point, sorry, I forgot to explain the condition if cross is greater than 0. So if cross is greater than 0, then the input I point will make a greater angle than the random point. So we just assign random to be input I. And then why we cleared this collinear is, suppose if there were any elements in this points in this collinear, now we have found out a better point, right? So with a better inclination, so all those points are not a part of the optimal layer, right? So we just need to clear them off. They should not be discarded because they are not a part of the line segment of the optimal layer. Okay, so now we just erase it, and then so since random is the most optimal, we just push back the random to the current layer and then erase the random from the set. And now again, as explained in the video, we repeat the same process with new current as the random one. And as explained in the video, if we just complete one rotation, we just break out of the loop. So this is the process of forming one layer. Okay, so now as you can observe, like what happened is the first point got inserted twice. One was before the while loop started, one was here in this line number 134, I guess. So it got inserted twice. So for that, we just pop it back and erase it if it's present. Like what happens is, sometimes the for loop is not executed because there are only one element. So in that case we need to erase it. So I gave another erase, and then so now we have the complete layer with us. So we push back the layer. So in all layers store all the individual layers. So we push back the layer, and now we just empty the layer vector. So now it's time for query. So in each query we are given a point x and y, and then so as explained in the video, we are iterating through all the layers, right? So starting from the outer layer we go, and then I just take one layer at a time in this clone vector. So if the size of the layer is less than or equal to 2, then we can't do, like, there's not even a triangle forming, then there's no point in enclosing any point, so we just break. So for every line segment we are just checking the cross product. If the cross product is greater than 0, that means the point is lying outside, and then so it doesn't satisfy the condition, we just break apart. There's no point in checking the further line segment as explained in the video. And if answer is true, we just increase the total number of layers, else we just break up. Okay, so let's just execute this program and check it if it runs well or not. So it's compiling well. Let's just submit it and check it. So as you can see, all the test cases have passed. So yeah, there are a few other algorithms to do it. So but I think this was very simple, just involving cross products. And technically these layers are named as convex cell. In convex cell, you find like you can search on the net. And this I think this algorithm is named as Jarvis March algorithm. The process of finding the constructing the layers is called as Jarvis March. There are other algorithms called Graham scan, but what we want to show here is uh, those algorithms really involve simple concepts like cross products. There's nothing complicated, no other data structure to be learned separately for this. So all this revolve around basic concepts. So that's it for the video. Thanks guys for watching this video.